Hi, we're the Carleton Planetary Robotics team, and this is our submission for the 2025 University Rover Challenge. After submitting our first rover to URC since 2019 last year, CPRT went on to compete in the Canadian International Rover Challenge, where we placed 7th overall. Since then, the nearly 100 active undergraduate members from all disciplines of engineering, as well as computer science, biology, and IT, have worked on designing an entirely new rover for the 2025 competition based off of what we learned last year. Broken into subteams of mechanical, electrical, software, and science, each team took a requirements-based approach, working backwards from the challenges outlined in the rulebook and integrating those requirements into the fundamental design of the rover. It is my pleasure to introduce to you our 2025 competition rover, Spike.
Taking what we learned at competition last year, the mechanical team's primary design goals were to reduce weight and become simpler without sacrificing strength and capability. From this, we decided to do an entire redesign of our mechanical system. This let us develop and produce simple yet effective chassis and arm designs. The frame was redesigned to be made out of flat plate aluminum rather than the bulky aluminum extrusion. This allowed for a much smaller footprint as well as easy mounting for the electrical components with modular mounting for the science and arm modules. The team opted for a 4-wheel drive rocker suspension with a transfer bar to ensure stable driving and maximum traversability. The mounts for the suspension were integrated directly into the frame for effective load distribution. Moving down to the wheels, we were able to reduce the weight of each wheel by roughly 2 kilograms through use of a much lighter wheel and wheel mounting system. The 3D printed TPU wheels allowed us to go with a lightweight design that is optimized for support and traction over many different Mars-like terrains.
Moving to the operations side of the rover, one of our key areas of improvement over last year was our communication architecture and video streaming capabilities. With improvements made to our long-range communication system, we're able to reliably stream 1080p video back to the operations center at distances up to 1 kilometer away in low-noise environments. Along with this, the accuracy of our GNSS system was improved with the use of RTK, giving us a positional accuracy of 20 centimeters and a heading accuracy within 1 degree.
This year on the software subteam, we're going to be abstracting away all of our modules, including autonomy. This change will allow us to quickly change configurations with minimal downtime between systems. For autonomous navigation, the rover generates a path using the SAR algorithm with a hybridized pure pursuit kinematic controller to minimize point turns and optimize for skid steer dynamics. To generate a safe path, the point cloud from the onboard stereo camera is used to create an elevation map of our surroundings. Then a custom algorithm is run to identify the traversability cost based on the slope and edge detection. When outdoors, the visual odometry can be fused with GNSS data to generate a global map and keep track of historical cost for beyond line of sight path following. For object detection, the team used a ResNet deep learning model, which was trained on over 100 images to detect specific objects like a hammer, as well as generalized classes such as water bottles.
The autonomous control continues to the arm with full inverse kinematics of all 6 degrees of freedom with absolute encoders at the primary joints, and a solenoid in the end effector for fine planar movements. For non-autonomous operations, the end effector is equipped with an HD camera, a laser pointer to assist in centering, and a view of the arm from the rover itself. To achieve the accuracy required for the competition tasks, linear actuators were used on the main joints. This allows the arm to be repeatable within 2 centimeters at full extension. The end effector was designed with an encompassing grip, allowing it to close flat for small objects while also gripping around larger objects. The tips of the end effector can be quickly swapped out depending on the mission requirements. The arm was designed to be easily removed and replaced with a science module using the same power connectors and mounting points.
With this being our second year back, the science team has taken what we learned from our win at the Canadian International Rover Challenge and completely redesigned our science module for URC. This year, the science team has chosen to focus on simultaneous extraction and analysis to cut both time and weight from our approach to the science mission. Operation is broken down into 3 actions: drilling, surface analysis, and subsurface analysis. The sediment from above 10 centimeters is collected in a chemical analysis chamber where an HCl assay is performed. This will let us know if the rocks we are looking at are carbonate rich. Once a depth of 10 centimeters is achieved, the sediment is diverted into our collection unit where it is cached. While drilling and subsurface analysis occurs, the surface analysis can commence. This analysis includes our custom-built microscope and Raman spectrometer. The team will perform Raman spectroscopy on a surface sample to search for biological molecules, primarily carotenoids. A 785 nanometer laser was chosen because it provides the best balance between scattering efficiency and minimization of background fluorescence. The microscope will be used to take close-up, well-focused images of the sediment to determine the mineralogical makeup of the site and look for evidence of past depositional environments.
To power all of these missions, the electrical team redesigned the power and communications architecture this year, opting for a 24-volt drive system with all devices communicating over campus. This change also allowed us to redesign the power delivery board, cutting the board size in half and implementing relays on each output to allow for remote resetting of each device individually. The electrical team has also begun several multi-year R&D projects, including a custom flight controller for a future drone and a brushless motor driver to replace all our off-the-shelf controllers.
Thank you for your time, and we hope to see you at URC.